I believe that. Okay. So today we're going to look into examples of centric symmetrical pure bending, and then we're going to look into sandwich material. Okay, so last week we did quite intense theory on pure bending. So as you can see from your screen now, is all this structure, the cross-section view, cross-section 1, 2, and 3, they are known as symmetry bending. Okay, they are classified as symmetry bending, and this is because stress alpha is equal to stress beta for all of them, and stress I is equal to stress J on all of them. So the stress symmetry, okay, symmetry over here means stresses about the vertical axis, where the stresses on the left hand side is equal to the right hand side. Nothing to do with the centroid. Okay, the centroid is just making you comment. So where I drew the pink line, that is the axis of symmetry for your stresses. Okay, so the symmetry bending is highlight again is due to your stress view. So we classified this as symmetry bending. Okay, nothing to do whether the cross section is symmetry or not. Nothing to do whether is the structure is loaded symmetry or not. Okay, nothing to do with that. It's all based on stress view. So today we are going to more detail, okay, on example number 1. So example number 1 is you have a 60 Newton meter couple, okay, or moment. You have a second moment applied to a steel bar, assuming that the couple is applied about the z-axis. So this is your z-axis over here. Determine the shearing stress. Okay, let's ignore the radius of curvature for now. Right? So we have to determine the maximum stresses. And then we are going to solve part A, assuming the moment has been shifted to the y-axis already. Okay. So I want to highlight two things over here. Okay. So when it is, so for the first part A, the moment, right, is on the z-axis. Okay, the moment is on the z-axis, and then we are aware that this will be your x. Okay, wrong color. I do apologize. We are aware that this is your x. Okay, so whatever we calculate is in the x direction. Whatever we calculate, the normal stress is in the x direction. So for mz, so okay, so moment, so mz means moment about the z-axis. Okay, moment about z-axis. We are still going to calculate stress x, right? Is equal to mz over izz multiplied by what? Y. Okay, so that's for part A of the question. Then we go into part B of the question, right? Part B of the question. So part B of the question is now the moment is shifted to the what? To the y-axis. So again, so we are going to do for my, which also correspond to the moment applied about the y-axis. Now, mind you, our stresses, the stress direction is still in the x direction. So stress x. So now this will be equal to my divided by Iyy multiplied by z. So a lot of times students get confused how to calculate Iyy or how to calculate Izz and Iyy. They got mixed up. Okay, they got mixed up, and then when you mix things up, okay, you're done. Okay, you're game over. And also make mistake regarding what is Y and what is Z. So I'm trying to come up with a technique for you to identify this with minimum error. Okay, that I want you to have that confidence, because if you don't have the confidence in this, when we go into unsymmetric bending, okay, we're done. Okay, we're done. So this is the foundation. Okay, so okay, let's start from here. So we're going to calculate. So far, anyone any questions so far? We're okay. Okay, so we're going to calculate the stress. Okay, we're going to calculate part A. Right, part A. So part A is the moment is about the z-axis. So now looking at the transformation, okay, looking at the transformation, we're going to review the structure this way. So we're going to review X, okay, Y, and then we have our rotation about Z. Okay, so this is our wall. Okay, and then this is our structure. Okay, so there's our structure, and then the structure is, this is the moment arrow. Okay, so you use the right hand rule, your thumb point to the page. Okay, so the moment vector, so this is M in the Z direction, right? Why Z direction? Because if you look at this curvature over here and this curvature over here, right, they have the same like orientation in terms of curvature, yes or no? So that's where we call this MZ. Okay, so like what I taught you guys before, right? Did I teach you guys before last week? Did I? Maybe not. Okay, probably last week I did not touch into this. So a good thing to remember, okay, a key thing to remember is the head of the moment arrow. The stresses are always in compression. And the tail end of the arrow, of the moment arrow, is always in tension or tensile. So because of the moment, so if you look at how the structure is deformed, the structure will deform this way. Okay, I'm going to sketch this out. So this is how the structure will deform, right? So this is how the structure will deform. And then if I call this point over here as alpha, this point over here as beta, right? We know that point alpha is going to be in tension, right? Because the radius of curvature, at alpha, which is this curvature over here, has a wider circumference than the curvature on the inside one, right? This one have smaller circumference, right? So it's in compression. Okay, so beta is in compression, alpha is in what? It's in tension. Okay, so from here we know that we are going to calculate stress X over. I'll write this out. I'll write this out. So based on from the moment, from the bending moment vector, okay, the head of the arrow is compression and tail is in tension or tensile. Okay, So now the formula that we're going to apply is stress X is equal to mz over izz multiplied by y. Okay. So we're going to draw this out now. Okay. So we're going to view at a cross. So we're going to have a cross sectional view. And my cross sectional view, I'm going to view it at the end, where this will be my y. Over here, this will be my z, and this is my rotation in the x. So we are now at this structure. We are viewing from here. So this is my I. Okay, we are viewing from there. So it's 12 by 20. Okay, so there's a cross section. So I'm gonna draw it big so you can see better. Right. So this is our cross section. So we are aware. We know that this line over here is your YY line. And this line over here is your ZZ line. Okay. So we want to find IZZ. Right? Why IZZ? Because moment about Z, the second moment of area will be about the Z-axis. Okay. So IZZ is equal to width, depth, cube, divided by what? 12. So what is our width and what is our depth? That's where the problem comes. Okay. So we know for this case, we want to find IZZ. Okay. So any geometry that is parallel, so geometry parallel to Z axis is always the width, right? So this is always the what? The width. Any geometry that is parallel to the ZZ axis, which is what we're going to find out, will be the width. And then any axis or any geometry, right, perpendicular to your ZZ axis. So geometry perpendicular to the Z axis is always the depth. Yeah, you can see. So this direction will always be the depth. So you will never be confused or not. What is the width? What is the depth? Nothing to do with English. Okay, don't be like me. When I was undergrad, I did my undergrad in the UK. I thought it was English. Oh, width is always this, depth is always this. No, nothing to do with English. Okay, don't be a fool like me. So from here, we know that this is 12 millimeters, and the depth, right? The depth is 20 millimeters, right? So we can immediately calculate that our IZZ, the width is 12, the depth is 20, power 3 divided by 12. Okay. So 20 power 3 times 12 divided by 12. So it's equal to 8,000, or 8 times 10 to the power minus 8 times 10 to the power 3 millimeter 4. Okay. Or 8 times 10 to the power minus 3. Then you do plus 3. Okay, plus 3. Then you do a minus 12. Why? To convert to meter, is 4 multiplied by minus 3. Okay, so that's why minus 12. So 4 times 6 is minus 12. So this will be 8 times 10 to the power minus 9 meter 4. So this is to help you in your unit conversion.